still in Chapter 12 on the sum product algorithm. I hope to get through that today fairly expeditiously and to start with Chapter 13. The handouts for today will be Chapter 13, and as usual, problem set 9 with problem 8.3 has been moved up into problem set 9, and problem set 8 solutions for 8.1 and 8.2. I'm going to start off on a different tack of presenting the sum product algorithm. Where is everybody? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is there any competitive event that I should know about? It's just, I know the traffic was bad and it's a rainy late morning. Problem getting here myself. Well, this is improving. The write-up of the sum product in the notes is in terms of equations. As I've never been terribly satisfied with this write-up, it's concise, but we have to invent some new notation, which I don't consider to be completely transparent. I've never found it particularly easy to present in class, and it's been a little frustrating to me. So I'd like to try a different approach. I'd like in class just to go over through a very explicit example, our favorite 844 code, what we're trying to achieve with the sum product algorithm and how the sum product algorithm helps us to achieve it in an efficient way. So it's proof by example. It won't be very satisfying to those of you who like to see real proofs, but that you can get by going back and rereading the notes. So I'm going to try doing it this way, and you will let me know by your looks of gladness or of frustration whether you like it or not. So let's start at the beginning again. What are we trying to do? We're trying to compute the a posteriori probability of every possible value of every symbol, internal and external, that appears in a graphical realization for a code. And we will consider these to be APP vectors. In other words, if a symbol is 8 valued, there will be 8 APP values in the vector. And we're going to assume that we have a cycle-free graph realization so that we can proceed by the cut set idea to solve independent parts of the graph. And at the very end, we'll relax that and see whether we can still do okay. All right, one concept that seems very simple in theory, but that some people don't get till they really try to do it in practice, is that an APP vector is really a likelihood weight vector normalized so that the sums of all the probabilities are equal to 1. For instance, if we send +1 or -1 through a additive white Gaussian noise channel with sigma squared equal to 1 or whatever, then the probability of, we call this y and this r, the probability of r given y equals whatever, let's just write probability of r given y is 1 over square root of 2 pi sigma squared e to the minus y minus r squared over 2 sigma squared. And so we can compute that for y equals 1 and y equals -1. And we'll get a vector of two things. The APP vector would then consist of this evaluated for y equals 1. And let me just take this part of it, e to the minus r minus 1 squared over 2 sigma squared, and e to the minus r plus 1 squared over 2 sigma squared. something proportional to these two vectors normalized, and that's why I continue to use this proportional to symbol, which you may not have seen before, or maybe you have. So the APP vector in this case would be proportional to, well, actually 1 over square root of 2 pi sigma squared times each of these two things. But this would basically tell you how much weight to give to +1 and -1 as possible transmitted symbols. And all that matters, there's one extra degree of freedom in here. You can scale this by the whole vector by any scale factor you like, and it gives you the same information, because you can always normalize the two terms to be equal to 1. So if this, for instance, was 0.12 and this was 0.03, that's equivalent to 0.8 and 0.2. Two probabilities, actual a posteriori probabilities that sum to 1. All you got to do is keep the ratio right. This is 4 times as large as that, so what that really means is 0.8 and 0.2. And in implementations of the sum product algorithm, we never really worry about constant scaling factors. As long as they appear in every term, we can just we can forget about scaling. I mean, we don't want things to get too large or too small, so we can apply an overall scaling factor. But as long as we've got something, the relative weights, then we have what we need to know. Okay. So let's go to the 844 code, since we know that very well, and ask ourselves what it is we're trying to compute. We're given APP vectors for each of the 8 received bits. Let's say we transmit Y, we receive some R, perhaps over an additive white Gaussian noise channel. So we get a little 2-term APP vector for each of these Y's, telling us the relative probability that 0 was sent or a 1 was sent. All right? That's called the intrinsic information. And let me just call that. So for each one, we get P0 and let me make it P0 and Q0, the 2 terms for Y0, P1 and Q1 for Y1, and so forth. So we have that information for each of the received symbols. What's the likelihood of each of these code words then, given these individual bitwise likelihoods? The probability of the all 0 code word, its likelihood, let's say, is then proportional to P0, P1, P2, P3, P4, P5, P6, P7. Whereas the probability of 1111, 0, 0, 0 is Q0, Q1, Q2, Q3, P4, P5, P6, P7, so forth. Each one is a product of the 8 corresponding terms. Yes? Yes?
You're assuming that the bits are independent.
Yes, it's a memoryless channel. So the noise in every symbol transmission is independent. And that's important too.
What I mean is the second bit transmitted is independent of the first bit transmitted.
I'm sorry, I was writing and I missed what you said.
No, I mean, if the first bit is 0, maybe there is a code where if the first bit is 0, the second bit has to be 0.
Yeah, there's certainly dependencies among the code words. That's what we're trying to take into account. This is how to take it into account. So I'm assuming a memoryless channel, but I'm, of course, assuming dependencies within the code. All right, how do I do that? One way is maximum likelihood decoding. What do we do when we do maximum likelihood decoding? In principle, we exhaustively computed each of these 16 products, each of these 16 likelihoods for each of the 16 code words. We'd simply pick the one that's greatest. And that's the code word that is most likely to have been sent, right? So that's what exhaustive maximum likelihood decoding consists of, finding the maximum likelihood word. All right, and that clearly takes into account the dependencies. We're only considering valid code sequences when we do that. Okay? In APP decoding, we're doing something else, but it can be characterized quite simply. What's the a posteriori probability that, say, the first bit is equal to a 0 or is equal to a 1? We can get the APP by summing up the likelihoods of all the code words that are associated with the value of the bit that we want to see. So we take the 8 code words that have a 0 in this place, and we'd sum up these likelihoods for those 8 code words, and that would be the weight, the likelihood weight of y0 being 0, and the likelihood weight of y0 being 1 would be the sum of the other 8. And again, you see that scale factors aren't going to matter here, so all we want is the relative weights of these things. So that's what we're trying to do in APP decoding, but we're trying to do it now for every single variable. At this point, I've only shown you the symbol variables, the external variables. So a brute force way of doing that would be to fill out this table, all 16 likelihoods, do these sums, and then we'd have the APP vector for each of these, right? Now we're looking for a more efficient way of doing this. The efficient way of doing this is going to be based on the fact we have a cycle-free graph realization, which in this case is a trellis realization. I'm going to use this two-section trellis where each section is a 4-tuple. Okay, we've drawn it in 2 different ways. This is a very explicit way showing the 2 parallel transitions that go from the initial node to the central state, and then 2 more down here. The set of code words is the set of all possible paths through this, corresponds to the set of all paths through this trellis. So, for instance, it includes the all 0 word, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, and so forth. And these I happen to have listed as the first 4 here. All right. Or we now have this more abstract way of writing this same thing. This says there are 4 external variables and 2 state variables, or a vector space of dimension 2 here and a vector space of dimension 4 here, that the dimension of this constraint is 3. That means there are 8 possible values for these combinations of 4 and 2. They're shown explicitly up here, and they form a linear vector space. Okay, so either way, this is our trellis realization. Now we know that based on to do maximum likelihood decoding, it's useful to have this trellis realization. Because, for instance, we can do Viterbi decoding, and that's a more efficient way of finding what the maximum likelihood sequence is. Basically, because we go through, and at this point we can make a decision between 0, 0, 0 and 1, 1, 1, 1. All right? We only have to do that based on this 4-tuple, and then we can live with that decision regardless of what else we see in the other half, and likewise in the other direction. Okay? So now we'd like to use the same structure to simplify the APP decoding calculation, which looks like a more complicated calculation. So how do we do that? We introduce 2 state bits here. All of these have state bit 0, 0, 0, 0. This point, we've called this state 0, 1. Just to keep it visually straight, 0, 1, 0, 1, 0, 1, and then there are 8 more corresponding to the other 2 possible values of the state bits over here. Okay, and now this is a quaternary variable. We want it to assume that it's a 4-valued variable, and to make the realization cycle-free, I don't want to consider it to be 2 independent bits. So there are 4 possible values for this state variable. Maybe I just ought to call this my state space. Okay, which is a 4-valued state space. Now, what's the a posteriori probability of the state being, say, 0, 0? I compute that in the same way. I compute that simply by summing up the 4 likelihoods of the code for the external variables, the code words that are associated with these state variable 0, 0, the first possible value of this quaternary variable. All right, so it would be the sum of these 4 things. Yes?
State there 0, 0, and what about?
I've only listed half the code words. There's only 8 of the 16 code words. You want me to write the other 8? Okay. And by the way, there's at least an implicit assumption here that the code sequence determines the state sequence. As we found when we did minimal trellis realizations, the code sequence always does determine the state sequence. So if I know the entire code word, that also tells me what the values of all the state variables are. There's a 1-to-1 correspondence between code words and trajectories in a minimal trellis. I believe I'm sometimes implicitly using that assumption. But anyway, it holds whenever we have a cycle-free graph. On a cycle-free graph, we have a well-defined minimal realization, and the minimal realization does have this 1-to-1 property. So the state variables are determined by the symbol variables. Okay, so suppose I want to compute the values of these state variables here. Let me write this out. This will be P0, P1, P2, P3, Q1, Q4, Q5, Q6, Q7, and then there's one that's all Qs. Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. So basically what I want to do is take the sum of these 4 things. And that's just a sum of products, and I could just do it. But the Cartesian product lemma gives us a simpler way of doing it. We notice that I can have either of these 2 4-tuples as a first half, and either of these 2 4-tuples as a second half. In fact, I see over here explicitly these 4 code words are the Cartesian product of 2 4-tuple codes. All right, the repetition code on 4. Okay, so I can use the Cartesian product lemma to write this as, again, let me write it very explicitly, P0, P1, P2, P3, which you recognize as the probability of this 4-tuple plus Q0, Q1, Q2, Q3, the probability of this 4-tuple, times P4, P5, P6, P7, plus Q4, Q5, Q6, Q7. Now, do you agree that the product of those 2 terms is equal to this? The sum of these 4 terms. Yes, there are 4 terms in this sum, and they're what we want. And it's because we have this Cartesian product structure, which we always have in the state space. This is the basic Markov property of a state variable. All right. So that's a simpler calculation. All right. This requires 4 multiplications. Each one is a 7-fold multiplication. This only requires requires 1, 2, 3, 4-fold multiplications plus 1 overall multiplication. And, it's certainly a simpler way to compute that. Okay, and I can similarly do that for each of these down here. So, what this leads me to is what I called last time the past-future decomposition. We have one APP vector over here that corresponds to the, let's call it the APP vector of the state given the past received symbols. We had something like that. Okay, in other words, given what was received for y0, y1, y2, y3, what's the probability, the partial a posteriori probability for each of the 4 possible state variables given this past? All right? And similarly, we have another vector, which I will consider to be a message coming in this direction, a message consisting of a vector of 4 values, which is what's the probability of this state vector given these four received symbols, which is computed in the same way. That's this here. And the past-future rule is that just the overall probability for any of these internal state variables, the overall APP vector, is just obtained by a component-wise multiplication. This would be the APP of the state vector being equal to 0, 0 given the past. This would be APP of the state vector given 0, 0 given the future. We'd have the same thing for 0, 1, 1, 0, 1, 1. And to get the overall APP vector given all of the rule is just multiply them component-wise. All right, we take the likelihood weight for 0, 0 given the past and multiply it by likelihood weight of 0, 0 given the future, and that gives us the total likelihood weight up to a scale factor. Okay, and the notes derive this in equation term. You see it basically comes from this Cartesian product decomposition, which we always get for any internal state variable, that the possible code words consistent with that state consist of a certain set of possible past code words consistent with that state, Cartesian product with a set of possible future code words consistent with that state. And as a result of that Cartesian product decomposition, we always get this APP vector decomposition. That's what the proof says in the notes. Do you like this way of arguing? A couple of people are nodding at least. It's an experiment. All right, so that tells us what we're going to want to do, at least for the internal variables, and actually the same is true up here. The variables going in are easy. That's just P0, P1, P2, P3, or whatever. The ones coming out are, this is called the intrinsic variable, the one that we get from direct observation, the intrinsic APP vector, excuse me. The extrinsic APP vector is the one that we get from all the rest of the inputs and symbols in the other parts of the graph. And we combine these component-wise to get the overall APP vector. All right, but we now have to do this for every part of the graph. Let me go through another calculation which will, how do we, for instance, find the APP vector for y7, the extrinsic APP vector for y7, given that we have a trellis like this? Okay, in general for y7, we're going to be adding up all the zeros, these guys, and 4 more down here, and we'll make that the extrinsic APP vector of 0. So we want to add up this and this and this and this and so forth, 8 of those. We want to do that in an efficient way. What are the set of all? This defines a code word with 8 possible components. Let me move this up now. So let's talk about this 6.3 code. What does it look like? With state vector 0, 0, I can have y4, y5, y6, y7 be 0, 0, 0. Or I can have it be 1, 1, 1, 1. With state vector 0, 1, I can have 0, 1, 0, 1, or I can have 1, 0, 1, 0. With state vector variable 1, 0, I can have 0, 0, 1, 1, or 1, 1, 0, 0. And with 1, 1, I can have 0, 1, 1, 0, and or 1, 1, 1, 0, 0, 1. All right, so that's precisely the 6.3 code I'm talking about. Now, suppose I have the APP vector for each of these. The APP vector for each of these, 0, 0, we've already calculated, be P0, P1, P2, P3, plus Q0, Q1, Q2, Q3. That's the likelihood vector for 0, 0 coming from the past. All right, so that's this message, one part of this message here. For either of these, I get, I don't know, P0, Q1, P2, Q2, Q3, plus Q0, P1, Q2, P3, reflecting the 2 possible ways I can get to this value. All right, so those are going to be I'm going to get 4 terms that I've computed for the past message. I'm going to have 4 likelihood weights corresponding to each of the 4 values of this state variable. All right, so I've got that vector. I already computed it as part of the computation to do the APP for here. It's the past part of it. All right. So now I want to compute the probability that y7 is a 0. All right. The rule here is to take every combination in this code, and again, I'm going to get well, let me write this part of it. This is going to be P4, P5, P6, P7. That's the probability of this 4 tuple. This is Q4, Q5, Q6, Q7. This is P4, Q5, P6, Q7, Q4, P5, Q6, P7, and so forth. That's the weights I want to assign to each of these. So now I get a weight for each of these 6 tuples. I multiply this by this to get the weight, the likelihood weight for this code word, this by this to get the likelihood weight for this code word, and so forth. And I add these to buckets. I simply go through this, and I'll add this one to the bucket for y7 equals 0, and I'll add this to the bucket for y7 equals 1, and this to the bucket for y7 equals 1, and this to the bucket for y7 equals 0, and so forth. All right. Now, it's clear that in this bucket, I'm always going to get the same value for P7. I'm always going to get a P7 for 0 and a Q7 for 1. So just looking at y7, I don't have to compute the 7th value here. So if I did this separately as a little y7 variable, then the incoming message, the intrinsic information, would just be this P7, Q7 likelihood weight vector. Okay? And what I really want to compute is the outgoing part, which has to do with y4 through y6. So let me draw it that way. I'm sorry if this I don't think is very good exposition, but bear with me. So now I'm going to put this times this in my bucket for 0, this times this in my bucket for 1, and so forth. The question here is, does this method give me the same method as the answer is my exhaustive method up here? And again, because of the Cartesian product character of the states, you can convince yourself that it does. In other words, I can use this as a summary of everything in the past that got to the state value equal to 0, 0, 0. Any time I got to 0, 0, 0, I got it through one of these two things. And so for any possible continuation over here, I could have got to it in one of these two ways. And I'm going to find terms, e.g., these two terms. Let's see. What do I want? I want two ways of getting to 0, 0, 0. I'm sorry, these two. I claim that this times these is equal to the sum of these two. And it is. You know, I can get to 0, 0, 0, 0, 0 either through this or this. And I can get to 1, 1, 1, 1, which is this one, either through this or this. And again, it's a fundamental property of the state that whenever I get one of these, I'm going to get both of them in equal combination. All right, so I can summarize things in this way, which leads to an efficiency of computation. So what I'm basically explaining to you now is the sum product update rule. Which is how to propagate messages. Propagating messages, which are APP vectors. In general, my situation is going to be like this. I'm going to have some constraint code, NK. I'm going to have some incoming messages over here, which tell me about everything that's happened in this past, P prime, and in this past, P prime. Give me a summary of all the weights corresponding to that. I'm going to have some output symbol over here. And I want to compute now what the APP vector is for the possible values of this output symbol, which is going to be some aggregate of this down here. What I do is I go through all 2 to the k code words. Call this constraint code. Sorry, I'm using k again. That's 2 to the k code words. And compute the product of the inputs. Of input APP vectors according to the possible combinations of the input variables and the output variables that are allowed by this constraint. Okay? That's explicitly what I'm doing here. Here are all the possible combinations of state variables and symbol variables that are allowed by this 6.3 constraint code. There are 8 of them. All right? For each one, I'm going to compute the relevant product of APP vectors, and I'm going to add it to a bin. So add to a bin, bins which correspond to, draw it like that, output. I'm calling this the output variable values. Okay, and that'll give me the summary APP vector of the outputs for now the past, which consists of everything that could have happened in this side of the graph. Okay, again, I'm using the cycle-free assumption in several ways. I'm saying that everything that happens up here is independent of everything that happens here. Everything that happens completely in this past, it's just the sum of what happens here, subject to this constraint, and it has nothing to do with what happens over here in the future. Okay, eventually I'm going to do the same thing in the future. I'm going to compute a future component that's based on all this stuff. I'm going to get messages going in each direction, and I'm going to sum them up. Okay, now I'm seeing a fair amount of puzzlement on people's faces. Do you get abstractly what I'm trying to do here? Does anyone want to ask a clarifying question? Okay. So now, output variable values. I'm sorry. I think there's a little bit of confusion here because sometimes I've considered this output to be a 16-valued output. Here it's, in fact, well, it has 8 actually valid values. And if I was considering it that way, then I would just have one bin for each of these likelihoods. But now if I consider these as 4 binary variables, then I would aggregate these things according to the values of each of the binary values, and I'd get 4 vectors of length 2 for the individual APP, which is ultimately what I want here. So I'm sorry I've gone back and forth between subtly different realizations. Okay, I do find this very hard to explain. Perhaps there's someone else who can do a better job. You have a homework problem which asks you to do this, and I think having done that, you'll then get the idea. But it's a matter of going back and forth between the gross structure and the actual equations and just working it out. All right, so the key things in the sum product algorithm, I've already explained at some level 2 of them. We have this sum product update. That basically explains, given messages coming into a node, how do we compute the message going out of the node? We take contributions, products corresponding to what the code allows. We dump them into the appropriate bins in the output vector, and that's the sum product update rule. We have the past-future decomposition or combination rule. And that says, at the end of the day, you're finally going to get messages going in both directions, and you just combine them component-wise, as we started out with. And finally, we need to talk about the overall schedule of the algorithm. So let me draw an arbitrary cycle-free graph. Okay, suppose I have an arbitrary cycle-free graph. All right, consists of external variables out here, internal variables, and constraint nodes. Okay, how am I going to schedule these computations in order to do APP decoding of this graph? All right. Well, what do I have at the beginning? At the beginning, I measure the received variables corresponding to each symbol, and that gives me the intrinsic information, which is incoming message. You can consider from every symbol variable. You know, basically, what did I see on the channel? That's what that likelihood weight vector corresponds to. All right. What do I need in order to do the sum product update rule? I need the inputs. Think of this now as a directed graph, or I need the incoming messages on all of the incident edges on this node except for one. If I have all but one, I can compute the last one as an outgoing message. All right, so that's the structure of that update. So at this point, can I compute anything here? No. I would need the inputs, but I can compute this outgoing message. I can compute this outgoing message. I can compute this outgoing message. I haven't drawn these a very high degree. Normally we have degree higher than 2. If I had, you know, another input here, however, I could still get that output. All right. So that's time 1. Think of there being a clock, and at time 1, I can propagate messages into the graph to depth 1, if you like. There's going to be a systematic way that we can assign depths. All right, now at time 2, what can I compute? I can compute this guy, because I have this input. I can compute, now I have both inputs coming in here. I can compute this guy. Anything else? So maybe 0, 1, 2. I should put times on each of these so I don't get confused. 0, 0, 1, 0. And so this is 2 at the output. Okay. Now I'm at time 3. What can I compute? At time 3, I now have 2 inputs coming in here. I can compute this output. I actually, from these 2 inputs, I can compute this output at time 3. And from these 2, I can compute this outgoing message at time 3. All right, are there other things I can compute? Can I compute this? No, I don't have this yet. That's probably it. Does anyone else see anything else I can compute at time 3? Based on the time 0, 1, and 2 messages? No. All right, but I'm making progress, and it should be clear that I'm always going to be able to make some progress. At time 4, I can compute this message in that direction. Let's see, I now have everything I need to compute this message in that direction. And I'm almost done. And finally, I can compute this message in this direction at time 4, the extrinsic information for those variables. I guess I can do this at time 4. So I had that at time 3. And now at time 5, I can get everything else that I need. Time 5, I get that out. I get this out based on this input and this input, and I get this out based on this input and this input. So in a finite amount of time, in this case 5 computational cycles, I can compute all of the messages in both directions for every variable in the graph. And now as a final cleanup step, I simply component-wise multiply the vectors in the 2 directions, and that gives me the APPs for all variables. So this is a kind of parallel computation of all the APPs for all variables in the graph. And I claim 2 things. It's finite and it's exact. All right, and the exactness is proved from the equations and the cycle-free assumptions. So we can always decompose things as Cartesian products, independent components. The finiteness, well, I assume this is a finite graph. What is this number 5? It's really the maximum length of time it takes me to get from any any of these external symbol variables to any other external, from leaf to leaf in graph theory terms. And that's called the diameter of the graph. And again, some people count the last little symbol node, and some people don't count the last little symbol node. But it's clear that a finite graph is going to have finite diameter, and that the propagation time is basically going to be equal to the diameter. That's how long it takes to get across the graph. So each of these messages in each direction has a certain depth. That's the distance in the graph to the most distant leaf node. And the maximum sum of these is always going to be 5 in this case. Notice that it is a tiny little graph theory theorem. Yeah.
It's kind of easy to see why if you sum the messages flying through those past and future on the at one single edge, you would get the overall LDPC because you're summing the contribution from both the set of output symbols. But here on one of the edges, how do you prove that it will get you the overall LDPC of the symbols?
Right. Recall the state space theorem. Let's take any edge in here. Suppose we think about cutting it, a cut set through that edge. Suppose we consider agglomerating everything back here and calling that the past, agglomerating everything out here and calling that the future. So this is past and future. The idea of the state space theorem was that this is exactly the same situation as a two-section trellis. Because everything is linear, you get the state space theorem basically, which says that you get a Cartesian product of a certain past, a certain future. You get a minimal state space, which is kind of the total code modulo the part of the code that lives purely on the past and the part that lives purely on the future. That quotient space is really what it is, corresponds to the state space at this time. And this because every edge in a cycle-free graph is by itself a cut set, you can do this for every edge in any cycle-free graph. You can make the same arguments, so you get a well-defined minimal state space. You get a Cartesian product decomposition, which has a number of terms equal to the size of the state space, 2 to the dimension of the state space over a binary field. And so everything goes through just as it did in the trellis case. That was the argument. All right. So mushing all this together, you get the sum product algorithm. This is the fundamental reason why I took the time to go through minimal trellis realizations of block codes, not because that's actually the way we decode block codes all by themselves, or we even use block codes, we use convolutional codes. It's so that we could prove these very fundamental theorems about graph decoding. And we aren't even going to decode cycle-free graphs, so, but that's the intellectual line here. Okay, so thank you for that question. It was very well timed.
Now the only computationally sort of difficult task is at each code node, each node in the.
Okay, yeah. So let's take a look at the structure of this. Where do the computations occur? Every node, there's a computation. What's the complexity of that computation? It's somehow approximately equal to the size of the constraint code. We do one thing for every possible legitimate combination of variables, which is what we mean by the size of the constraint code. So if this is a 6-3 code, we need to do 8 things here, basically 8 multiplications. So, this in more general cycle-free graphs, that's what corresponds to branch complexity in trellis graphs. We found that the branch space corresponded to a constraint code in trellises. So the computation is basically determined by the constraint code complexity, and really overall what we'd like to do is minimize the constraint code, the maximum size of any constraint code, because that's going to dominate computation. All right, so we try to keep the K in these things as small as possible. Yes?
So then there is a trade-off between the constraint code complexity and the diameter of the parameter. You can agglomerate and get a larger dimension constraint code, but you have a shorter diameter. And so you can decode quickly.
Yeah, we're actually not too concerned about diameter. Because things go up exponentially with constraint code dimension, just that single parameter tends to be the thing we want to focus on. But we remember that's hard to minimize. In a trellis, we showed that, basically our only trick there after ordering the coordinates was sectionalization, and that we could not reduce the constraint code complexity, the branch complexity, by sectionalization. And then again, we build on that, and we went through this argument that said, gee, this corresponds to some trellis. We could draw a trellis where this literally was the past and this was the future, and the minimal size state space in this cycle-free graph would be the same as in that trellis. And what I guess I didn't show is that you can't reduce the constraint code complexity by significantly. Actually, I'm not sure there's a crisp theorem, but the fact that you now are constrained to size of state space, and this is certainly going to be at least as large as state space sizes, tends to indicate that you're not going to be able to do a lot about constraint code complexity by going to more elaborate cycle-free graphs than just the chain trellis graph either. And that's, I think, a missing theorem. It would be nice to have. I had a paper about a year or two ago. I'm not sure it ever quite gets to that theorem, but that's the theorem you'd like to see. You really can't improve this. So ultimately, we're bound by what you can do in a trellis, and in a trellis, you can't do too much about this branch complexity parameter once you've ordered the coordinates. All right, so we're, bit of hand waving here, but we're going to need to go away from cycle-free graphs. One reason I like normal graphs is that you get this very nice separation of function. You get the idea that nodes correspond to little computers. You could actually realize this with little computers. Put a computer in here for each node. Its job is to do the sum product update equation. And then, well, what are the edges? They're for communication. All right? These are the wires that run around on your chip. And so when we talk about state space complexity, we're really talking about something like bandwidth. How wide do you have to make these wires? All right? Do you have 6 bits or 9 bits or whatever? So state space really has to do with communication complexity. Constraint or branch has to do with computational complexity, which, sometimes one's more important than the other. Computational tends to be the thing we focus on, but we know more and more as we get to more complicated chips, communications complexity tends to become dominant. And this, of course, is the I/O. These are your pads which go to the outside world, your I/O pads. So it's really a good way to think about this. And in fact, some people, like Andy Loliger and his students, have experimented with building analog sum product decoders. The general idea here is that you can compute an output as soon as you have the 2 corresponding inputs. Well, all right, imagine another schedule where this thing just computes all the time based on whatever inputs it has. In a cycle-free graph, say you're in the interior, initially what you have on your inputs is garbage. But eventually you're going to get the right things on all your inputs, and therefore you're going to put the right things on all your outputs. So again, up to some propagation times, just putting in non-clocked little computers here whose function is to generate the right outputs given the inputs in each direction is eventually going to be right in a cycle-free graph. And in fact, there are very nice little analog implementations of this where it turns out the sum product update rule is extremely amenable to transistor implementation, nonlinear rule. So you just put these in, little computing nodes, and you put the right, you put whatever you received on here as the receive symbols, and you let it go, and it computes incredibly quickly for a cycle-free graph. Where we're going to go is we're going to say, well, gee, we got this nice little local rule that we can implement with local computers for the sum product algorithm. Maybe it'll work if we do it on a graph with cycles. And on a graph with cycles, this kind of parallel or flooding schedule where every little computer is computing something at every instant of time is probably the most popular schedule. And again, you build an analog implementation of that, and it goes extremely fast, and it converges to something. All right, it just relaxes to something where there's a local equilibrium in all these constraint nodes, and therefore some global APP vector that satisfies the whole thing. So, I think this is a nice attribute of this kind of graphical realization. All right, a particular example of how this schedule works. The cycle-free realization that we care most about is the trellis. So the BCJR algorithm is simply the implementation of this sum product algorithm on a trellis. SP on a trellis. So, generically, what does a trellis look like? I guess I should allow for some non-trivial code here. So all trellises have the same boring graph. Okay? What is this schedule? It's a cycle-free graph, so we could operate according to this nice controlled schedule, compute everything just once. And how does that operate? We get intrinsic information that's measured at each of these symbols here. What do we receive on the channel? We put that through a constraint code, and we get here, well, let's give this a name. This is called intrinsic 0. Here is alpha 1, which is just a function of the intrinsic information at time 0. And we combine that with the intrinsic information at time 1, and we get alpha 2, and so forth. So we get a forward-going path down the trellis. If any of you knows what a Kalman filter or a smoother does, this is really exactly the same thing. This is finding the conditional APP probabilities of this state vector given everything in the past. All right. In Kalman filtering or smoothing, it's done for Gaussian vectors. Here we're talking about discrete vectors, but in principle, it's doing exactly the same thing. It's computing conditional probabilities given everything observed in the past. And so the diameter here is just the length of the trellis, basically. So this is IN minus 1, IN. And here we have alpha n. And when we have alpha n, finally in here, we can compute the extrinsic information based on alpha n. It's just extrinsic n. We combine these two, and we're done for that guy. Meanwhile, we have to compute the backward-going information on each of these branches. So we compute first Bn based on In, then we get Bn minus 1 based on In minus 1 and Bn, and so forth. So we get a backward-going propagation of conditional information. Each of these betas represents the a posteriori probability vector given the future from it. And finally, when we get down to here, we can compute extrinsic 0 from beta 1. And by this time, when we have both alpha 1 and beta 2 coming into here, we can, of course, get extrinsic 1. When we get both the alpha and beta coming in here, we can get extrinsic 2, and so forth. All right, so of course, you can write this down as equations. If you want to read the equations, you look in the original Ball, Koch, Jelinek, and Raviv article in 1973. This was, again, a kind of lost paper because just for decoding a trellis, the Viterbi algorithm is much less complex and gives you approximately the same thing. I mean, I talked last time how probably what you really want to do in decoding a block code is maximum likelihood. That's minimum probability of error on a blockwise basis. What APP decoding gives you minimum probability of error. If you then make a decision based on each of these extrinsic information or on the combination of these two to get the overall APP vector, that's called the MAP algorithm, maximum a posteriori probability. If you make a decision based on that, that'll give you the minimum bit error probability, but it may not necessarily even give you a code word, and it will not minimize the probability of making any error, which is generally what you want to minimize. So for trellis decoding of block codes, this was not favored. However, a block code as a component of a larger code, you want the APP vector to feed off to something else, and so with the advent of much larger codes, of which block codes are components or convolutional codes, BCJR is the way you want to go. And some people say it's about 3 times as complicated as the Viterbi algorithm. All right, so you'll have an exercise with doing that in the homework. There is a closely related algorithm called the min-sum algorithm, or the max product algorithm. And the idea of that is that you can really carry through the same logical computations, except when you get to one of these combining operations, rather than doing a sum of products, you can do a max of products, and that the Cartesian product law still holds, the same kind of decompositions that we have still hold. For instance, in this example, to get the state 0, 0, 0, before what we said we're going to get an APP vector where this is the past APP for the 0, 0 value of the middle state vector. We simply combine the likelihood weights of the 2 possible ways of getting to that state, and we sum them. All right, instead of doing sum, let's just take max. The maximum probability of getting, in other words, what's the best way of getting here? Same question as we ask in the Viterbi algorithm. All right, and we'll let that be the likelihood weight for the state vector. Otherwise, the logic is exactly the same. Similarly, coming this way, what's the max of these 2? Okay, what's the best way of getting to the state vector in terms of likelihood from the future? And what do you know? If we combine these things at this point, we now have a past vector and a future vector. Let's take the max of this times the max of that. That gives us the maximum likelihood way of going through the 0, 0 value of the state. Okay? So if we do this, if we do exactly the same logic for decoding this trellis, we get a two-way algorithm. It's like this. It's like the BCJR algorithm, where at every point we're computing the maximum likelihood. And it's not hard to show that what this gives you is that each of these symbols out here, it gives you the symbol that belongs to the maximum likelihood code word. All right, so how does it differ from the Viterbi algorithm? It gives you the same answer. It gives you the symbols one by one of the maximum likelihood code word. It doesn't have to remember anything. It doesn't store survivors. That's its advantage. Its disadvantage is it's a two-way algorithm. You have to start from both ends and propagate your information in the same way. And for block codes, maybe that's okay. For convolutional codes, that's certainly not something you want to do because the code word may go on indefinitely. So the Viterbi algorithm gets rid of the backward step by always remembering the survivor. It remembers the history of how it got to where it is, so that once you get the max, you don't have to. You simply read it out rather than having to. This backward part sort of amounts to a traceback operation. Okay, that's probably much too quick to be absorbed. But I just wanted to mention there is a max product version, which if you take log likelihoods becomes a max sum, or if you take negative log likelihoods becomes min sum. So this is called the min sum algorithm, and it does maximum likelihood decoding, whereas rather than APP decoding, and sometimes is used as an approximation, or there are intermediate approximations between these two.
The Cartesian product of the individual bits may not be equal.
No, if you use the min sum, basically everybody will converge on the same maximum likelihood code word. So all of these constraints will be consistent with the, you'd be taking a single max at each point, but at each point you will solve for the maximum likelihood code word, and what you'll see up here is the symbol that belongs to the maximum likelihood code word. This is maybe a bit of a miracle when you first see it, but you'll kind of independently get each of the bits in the maximum likelihood code word. Check it out at home.
Why not always do this?
Why not always do that? It turns out that we want softer decisions when this is part of a big graph. We actually want the APPs, the relative probabilities of each of the values. We don't. The max, in effect, is making a hard decision.
But it also gives the soft value of that.
Yeah, all right. It does give reliability information. So I'm not sure I can give you a conclusive answer to that question, except APP works better. That's a more empirical answer. Yes?
BCJR being intrinsically an APP kind of an algorithm, whereas Viterbi is a maximum likelihood algorithm.
Right.
Where does that flexibility of the input symbols being of not equally probable shows up in this algorithm? That we should be able to take that into account. Symbols are not equally probable. Code words rather, I'm sorry.
Yeah. Okay. Well, if the input symbols are independently not equiprobable, you can feed that in as, once they come out of the channel, once we see the channel information, the two symbols are not equiprobable anymore. So if somehow they a priori independently were not equally probable, you could just feed that in as part of this intrinsic information vector. That's almost never the case in coding. We do speak of this. The intrinsic information is sometimes regarded as a priori, and this as a posteriori, or the combination of the two of them is then a posteriori when this goes off somewhere else. But it doesn't really mean that the symbol itself was. It means that the evidence is biased one way or the other. And when this appears somewhere else in the graph, this will now appear somewhere down in some other graph. It's called the a priori information, but what it is the a posteriori information given all the received symbols in this part of the graph.
Another graph, let's say to do iterative decoding or something, then is the I0 of that other graph contain this a posteriori information added to it?
Yeah, the I0 for another graph is just the E0 of this graph. Okay? I mean, if you consider it all as one big graph, that's what you want. You want the message that goes in this direction, which basically summarizes all of the inputs from this graph. All right. In general, you'd have a little equals node here. You'd have the actual intrinsic information coming from the outside world there. You would compute the E0 from this graph, and at this point you would combine E0 and I0, and that would go around here. Okay, so the very last page of chapter 12 just says, okay, we've got a nice, clean, finite, exact algorithm that will compute all these APPs on a cycle-free graph. Now, suppose we're faced with a graph that has cycles. And here's the situation. Suppose the graph has cycles in it. Then, first thing that might occur to you, at least after this development, is, well, you know, we now have a local rule for updating at each of these computational nodes, each of these constraint nodes in this representation. Why don't we just let it rip? See what happens. You know, it's we're going to put in some intrinsic information at the outputs as before. We can compute some output message here based on, well, eventually we're going to get some input message from here. And we can compute some output message here based on all of these. And we'll pass that over. And let's assume what's called a parallel schedule or a flooding schedule, where in each cycle, every one of these little guys does its thing. It takes all the inputs that it has available at that time, and it generates outputs. All right? Well, hope for the best. It'll compute something. You can sort of intuitively see that it'll settle, it'll converge perhaps into some kind of equilibrium, or hopefully it'll converge into some kind of equilibrium. There's a basic fallacy here, which is that the information that comes in here, you know, is used to compute part of this message, which is used to compute part of this message, which ultimately comes back and is used to compute part of this message, and then part of this message again, so that information goes around in cycles, and it tends to be used again and again and again. Of course, this tends to reinforce previously computed messages. It tends to make you overconfident. You know, you heard that, you know, some rumor, and then the rumor goes all around the class, and it comes back, and you hear it again, and that tends to confirm the rumor, right? So it's that kind of telephone situation, and it's not really independent information. Intuitively, it makes sense that if all the cycles are very large, in other words, the rumor has to go to China and back, before you get it, that it probably is highly attenuated by the time you get it. Further, it's mixed up with all kinds of other information, so maybe it doesn't hurt you too much if the cycles are very large. And in fact, that's the way these capacity approaching codes are designed. Whereas, as I mentioned last time, if you're in a physical situation where basically your graph looks something like this, you don't have the freedom to make your cycles large, then this is probably a bad idea. And this isn't why in fields like vision, for instance, people try to use, this is the sum product algorithm is the belief propagation algorithm, if you've ever heard of that, widely used in inference on Bayesian networks. And the religion in belief propagation used to be is you simply can't use belief propagation on graphs that have cycles. Why? Because most of the cycles the graphs they dealt with look like this. In fact, it works terribly on that. So it was a great shock on that field when the coding people came along and said, well, we use belief propagation on graphs with cycles, and it works great. And this, as I understand it, really had an enormous impact on the belief propagation community. But it was realized that, gee, you coding people have it nice. You make your own graphs. All right? You make them so that this is going to be a very low-order, low-impact event. And that's right. But coding, we do have this freedom to design our own graphs. So we realize from the basic arguments that I put up before that we're really going to need to have cycles. As long as we have cycle-free graphs, we're going to get this kind of exponentially increasing complexity, which is characteristic of trellis graphs. So we're going to need cycles, but as long as the cycles are very long and attenuated, as long as the girth of the graph is great, maybe we can get away with it. And that, in fact, is the way the story has developed. And Gallagher basically saw all this back in 1961, but it took a long time for it to catch. Okay, so I didn't even get into Chapter 13. Chapter 13, we're going to first just introduce several classes, the most popular classes of capacity approaching codes, and then I'm going to give you some real performance analysis, how you would design, simulate, and these codes, and it's what people actually use. Okay, see you next time.